Assalamu alaikum guys. I hope you guys are doing well. Today's lecture for probability and statistics is Poisson distributions. If you recall, last time we studied binomial and multinomial distributions. Those were the distributions for discrete random variables. Similarly, the Poisson distribution is also discrete random variables. So this is a discrete probability distribution. So this is the third, you can say, distribution for discrete random variables. The Poisson distribution is used to model the frequency with which a specified event occurs. Okay, so Poisson distribution is used to model the frequency with which a specified event occurs during a particular period of time. For example, the total number of patients who arrive at an emergency room between 6 p.m. and 7 p.m. So see, there is a period of time associated with it, okay, and a frequency. Frequency is number of times something is happening. So number of patients who are arriving in emergency room between some time. Number of telephone calls received per day at some switchboard, or the number of alpha particles emitted per minute by a radioactive substance. All right, so see again, per minute, so there is time associated, per day time associated, and number of calls, number of particles, number of patients. So this is the frequency related to that. Now what is the formula? So if we have probabilities of a random variable x that has a Poisson distribution are given by the formula, probability of x is equal to x, e to the power minus lambda, e is the exponential, okay, lambda to the power x over x factorial. Now you see, as in the case of binomial distribution, this x is the question, right? When they will ask you the question, they will give you this x, right? So here e is universal constant, which is exponential. We know that it is 2.7183 and so on. This is an irrational number. So only lambda is missing. You see, the value of x will be given. It will be either 0, 1, 2, 3, so on. But lambda is missing. So this lambda is called the parameter. In binomial distribution, we had n and p as parameters. If n and p are given, we can give you the binomial formula. So here, if lambda is given, we can give you the Poisson formula. So the random variable x is called Poisson distribution and is said to have the Poisson distribution with parameter lambda. Okay, so if x has a Poisson random variable, then it has a Poisson distribution with parameter lambda. So only lambda is given, should be given here. In binomial distribution, you go from 0, 1, 2 up to some number n, because we repeat experiment n times. So at the most we can have n successes. Here there is no n mentioned. Why? Because it's the number, it's a frequency during some time. So we cannot predict how many patients we will get, how many calls we will receive. They can literally go to infinity. Right? So it means x can be very, very large here. It starts from 1 and it has no upper limit. Let's see an example. Some hospital keeps records of emergency room traffic. Okay, so those records indicate that the number of patients arriving between 6 p.m. and 7 p.m. has a Poisson distribution with lambda is equal to 6.9. So you see, in the question they gave us the distribution as well as the lambda. So this is very easy. So now he is saying that determine the probability on a given day, number of patients who arrive in this emergency room between 6 and 7 will be exactly 4. So this is my x, at most 2. Between 4 and 8, right? So these are x, these are the questions. So this is my lambda. So here he is asking me what is the probability that exactly 4 patients come in emergency room. So this is the question, probability of x equal to 4. At most 2. What does at most 2 means? X less than or equal to 2. At most 2, either can be 2 or less than 2. So 2, 1 and 0. Between 4 and 8, inclusive means 4 and 8 are included. So from 4 less than or equal to x less than or equal to 8. right? So these are the probabilities being asked. Okay, so now in D, I will come back to D part. Let me write the formulas first. So solution is, if X is my Poisson random variable, which is number of patients arriving between 6 and 7, then X has a Poisson distribution with parameter 6.9, because this is given to me. So the formula will become X is equal to X e to the power lambda and lambda to the power X divided by X factorial. Right? Now this X can go from 0, this X, small x can be from 0, 1, 2 and so on, right? Because no upper limit is mentioned here. So the first question was, what is the probability that exactly 4 patients come? It means I need probability of X is equal to 4. So e to the power lambda, lambda to the power X over X factorial, but now my X is 4, small x is 4. Okay, so if I put 4, you can use calculator. There is a button exponential in the calculator and there is a button of factorial as well. So if you simplify, your answer is 0.095. Similarly, what is the probability at most 2? At most 2 means X less than or equal to 2. Less than equal to 2 means 0, 1 and 2. All three are included. So see X0, X1 and X2. You can calculate them separately and add, that will be correct as well. But here you see e to the power 4, e to the power 6.9 is common in all these terms. So we can write it outside and just write these things inside, Okay, so now if you add these and just multiply by this number once, you will get the answer. If you want to do directly from this step, it will be okay. If you want to write your answer from this step, this will be correct too. Okay, because we have calculators, we can deal with these type of calculations. Third was between 4 and 8. Between 4 and 8, both inclusive, means 4, 5, 6, 7, 8. So again, you see x4, x5, x6, x7, x8. Right? So only x is replaced, remaining things are the same. So again, if you calculate and write the answer, it will be 0.666. Now what was the D part? D part was, he said, obtain a table of probabilities for the random variable x. Okay, now you know that because x can go to infinity, you see here I said x starts from 0 but it can go to infinity. So where should I stop? Right? So he said stop when the probabilities become 0 to 3 decimal places. Okay, so it means I will start from 0. So if x equal to 0, I can find the probability, it is 0.001. Why? I will put in the formula. So how I got this? I got this this probability came from e to the power minus lambda, right? Lambda to the power 0 divided by 0 factorial, because x is 0. Now if you put lambda 6.9, you will get this answer. You can try this. Then if you put lambda equal to 1, you will get this. If you put lambda equal to 2, get this. Keep on doing. Carry on. So where I have to stop? He said stop when your probability is 0 up to 3 decimal places. So here you see, when I reach 14, my probability is 0.006. So it is not 3 decimal places. Again, it is up to 2 decimal places. Up to 2 decimal places, it is 0. But when I put 18, I get 0.000 and then some number here. Right? But I'm not interested in that number. So this is almost 0 up to 3 decimal places. So here I will stop. I will not pick 19. Okay. So of course, usually in Poisson distribution, they don't ask you to create a table. But if they ask, you can create a table like this. In binomial distribution, we have upper limit. We know that x goes from 0 to n. So we will automatically stop at n. But in Poisson distribution, we don't know where we have to stop. So we will keep on calculating the probabilities unless some condition is given. Okay. Here the condition was given, stop when 3 decimal places give you 0. So we stopped here at 18. The last part was use part D to construct a probability histogram. Probability histogram is basically the bar chart, right? I told you at that time as well that some people call it probability histogram, but probability histogram is called bar or line chart. Okay, so you can make either bar or line chart, but if you combine all the bars together like this, you see I joined all the bars, so this is also called probability histogram as well. So what I will do, I will start with 0 and I will stop at 18, because you see my table is up to 18, from 0 to 18. So I will write x values on horizontal line and probabilities on vertical line. Okay, so these are the probabilities. At 0 we have this probability, at 1, at 2, at 4. So highest probability is, you see, at 6. I'm getting something here, 1.1 something at 6. So at 6 at 6 I got 0.151, right? So this is the probability 0.15 at 6. Okay, and then again it's going down and you end up at getting 0 at 18. 0 gives you 8, 18 gives you 0. So this is the probability histogram for this this discrete probability distribution. It's a discrete probability distribution. So he said predict, at the end he said predict the probability, the shape, identify the shape of this distribution. So it looks symmetrical but not very symmetrical. You see here it's not that down, and some tail is being made on the right, you see. So it's little skewed on the right. So it has a right tail, you see, it's going up like this, but here it has a tail. Okay, so it is right skewed. So what are the properties? Properties are something which are always true. So is there anything which is always true for Poisson distribution? So let's see. The shape of the Poisson distribution will always be right skewed. Okay, so in this case as well, you see it is right skewed. So this is not a coincidence. Poisson distribution will always be right skewed. Binomial distribution had all three shapes. We said if probability of success P is 1/2, it is symmetrical. But if it is more than 1/2, it will have right tail. If it is less than 0.1/2, it will be left tail. So all possibilities are there. But in Poisson distribution, it is always right skewed. All Poisson distribution are right skewed. Now the mean and standard deviation. If lambda is the parameter, then mean is the same as lambda. So in previous example, if I ask you what is the mean of this Poisson distribution, you will say that mean is 6.9. Why? Because lambda is 6.9. All right. So mean of a Poisson distribution is exactly equal to lambda, and standard deviation is square root of lambda. Square root of lambda. So as a matter of fact, if I write the variance is sigma square, right? Sigma square is lambda, and you see lambda is also mu. So in Poisson distribution, mean and variance are equal. Mean and variance are equal, but standard deviation is square root of the mean, square root of lambda. So in previous example, he said determine the mean and variance. So we can easily determine the mean and variance. Your mean is lambda, which is 6.9. Your standard deviation is square root of lambda, which is 2.6. All right. So it's very easy. Recall that what was the mean in binomial? NP. And what was the standard deviation? NP into 1 minus p square root. That was the standard deviation of binomial distribution. Now, sometimes what happens is when your n becomes very large in binomial distribution, if you recall, what was our binomial distribution? Formula NCX, p to the power x, 1 minus p to the power n minus x, where n is the total number of trials and p is the probability of success. When your n is very large, then it's very difficult to handle this. Okay, so when n is very large, it is often difficult or even impractical to use the binomial distribution. So what we do, we can use Poisson approximation for this. Okay, and how? Now you must be wondering, this is the binomial problem. How can I use Poisson? Because the shape of the Poisson distribution is different. But here we see we can use a Poisson distribution to approximate the binomial when n is large and p is small. When n is large and p is small. And there are two conditions. How large? When n is greater than 100 and the product NP is less than 10. So what we will do, we will check these two things. If these two things are true, then we can use Poisson approximation. And how we can use Poisson approximation? You know that the mean of the binomial is NP, right? And mean of the Poisson is lambda. So for Poisson probability distribution, I need lambda. But I know that the lambda is equal to mean of your distribution. And because in binomial distribution, my mean is NP. So it means I can take lambda as NP and use the Poisson distribution. So you see here I use lambda as NP. E to the power minus lambda, lambda to the power x over x factorial. So we replace this lambda by NP. So whenever your number of trials and probability of success are such that your n is greater than 100 and NP is less than or equal to 10, then instead of binomial formula, we can use Poisson formula and it will give you very, very accurate probabilities. Let's see an example. The infant mortality rate is the number of deaths of children under 1 year age per 1,000 lives during a calendar year. Okay, this is called IMR, the infant mortality rate. The people who are infants, like after their deaths, after their birth, if they die within 1 year, we call them, this is the infant mortality. Because this is the death of an infant. Children who are less than 1 year old are called infants, right? So he said, if I see how many children die per 100 live births, let's say 100 babies were born, and at the end of 1 year, 10 babies died. So 10 divided by 1,000 is the infant mortality rate. Now he said, from the word fact book, the CIA found that the infant mortality rate in Finland is a country in Europe, is 3.5. It means only 3.5 children die per 1,000 in a calendar year. So use the Poisson approximation to determine the probability that of 500 randomly selected births in Finland, there are no infant deaths, at most 3 infant deaths. You see, if this problem is written, I have two things. One thing is N is given and P is given. See, this is the rate, infant mortality rate, 3 by 1,000. So my P is also given. If I am interested in infant's mortality, then my P is 3.5 divided by 1,000. Okay, so this is my rate, which is 0.0035, I guess, right? So now N and P are given. So you know that when N and P are given, it's a binomial distribution, not Poisson. But now you can see that this N is greater than 100. This is one condition. What was the second condition? Find NP. So what is your NP? If you multiply NP, it is 0.35. Okay. NP is, N is not 100. N is 500. Sorry, I was struggling with 100. So if I multiply this with 500, it gives me 1.75. So let me erase this. If you multiply N and P, you will get 1.75. So 500 into 0.0035. So see, this is less than 10. This is what we want. These were the two conditions. N should be greater than 100 and NP should be less than 10. So both are true now. So you see, my N is 500, which is greater than 100, and NP is 1.75, which is less than 10. So it means I can use the Poisson distribution instead of binomial. Okay, so now what was the question? Question was, what is the probability that no infant deaths? So it means probability of X is equal to 0. So if I use probability of X equal to 0, this is my answer. And he said, at most 3 infants death. So at most means less than or equal to 3, right? So it means 0, 1, 2, and 3. So if I replace 0, 1, 2, and 3, this is my answer, right? X0 means this is 0, this 0. X1 means the power is 1 divided by 1. 2 means power is 2 divided by 2. 3 means power is 3 divided by 3. And because every term has e to the power minus lambda, so we wrote e to the power minus lambda outside. It's being multiplied with all 4 inside terms. Okay, so that's your answer. So this is the simple Poisson distribution. You see, it's very easy. You can do it directly if average, lambda is the average. So if average or rate is given, average rate is given, I can use Poisson distribution directly. If n and p are given but n is greater than 100 and p is less than 10, then again I can use Poisson distribution. All right, so there are two different scenarios where I can use Poisson distribution. So this is another example which is solved example. You can go through it. Okay, so again n and p are given here, and you can find n is greater than 100 and p is less than 10. So you can again use Poisson distribution and give the answers. Okay, so this is simple. So as in the case was binomial and multinomial distribution, at the end of the slides there were 3-4 questions, right? And here as well there are 1 2 3 4 5. There are 5 questions here as well. You can go through it and see if you can do it or not. Okay, so try to solve these questions, and if you have any problems, any difficulties you are facing, send me the questions. You can take the picture of your solved example and make an arrow. See, doctor, here I am having a difficulty, or I think that this solution is not correct, or whatever. So whatever kind of question you ask me, send me voice notes in WhatsApp group and mention the page number, mention the slide number, that here we are having difficulty. I will try to explain more. Hopefully things are going well so far, and you are understanding my video explanations of the lecture. I am posting these lectures on Moodle, as well as the video links are being sent on WhatsApp groups. So please try to do not wait for so long, because a lot of things are piling up, and of course all of your teachers are sending you the video links and stuff like that. So things are piling up. Don't waste your time. Spend as much time as possible and try to learn. Hopefully when we will come back, we will do more practice, and I think we have 3 weeks after we resume. So I will welcome any question from your side, and please try to watch the videos and try to understand the topics and ask me questions. So I'm done with the discrete random variables. We only had to do binomial, multinomial, and Poisson with discrete random variables. So in next lecture, I will start continuous random variables, and then I will study couple of continuous probability distributions as well. So till then, bye from me. Stay home, stay safe. Ma salam.